Hi, this is John Whitaker, and this is our fourth video for the Mathematical Analysis 2 course. And last time we were talking about if we had a max or min, local max or min, that the derivative, if it exists, had to be equal to 0 for that function, or we had a function defined from the closed interval from A to B and being a real value function. Today we want to look at some more consequences of the derivative. And the first thing we want to start off with is a version of the mean value theorem. As a matter of fact, I think this is called Cauchy's mean value theorem. Here's what it says. Okay, we start off with if F and G are continuous real functions on the closed interval from A to B, which are differentiable in the open interval from A to B, then there exists an exponent of the open interval from A to B at which f of b minus f of a times g prime of x will equal to g of b minus g of a times f prime of x. Okay, the proof, let f and g be continuous real value functions on A to B, which are differentiable on the open interval from A to B, we want to find an x in the open interval from A to B such that f of b minus f of a times g prime of x will be equal to g of b minus g of a times f prime of x. In order to help us do this, we will consider the following function. So consider h of x, or h of t, equal to f of b minus f of a, that times g of t minus g of b minus g of a times f of t. Now, since f of x and g of x are continuous, real value function, h of x, or I should say f of t and g of t, and h of t is continuous on a to b. Since f and g are f and g are differentiable, on open interval a to b, then h is differentiable on open interval from a to b. In fact, h prime of t will be equal to, it'll be f of b minus f of a times the derivative of g, and then it was minus, and it was g of b minus g of a, that's a constant, times the derivative of f. Okay, and what we're trying to do is show that there's this number x in a to b, such that f of b minus f of a times g prime of x equals to g of b minus g of a times f prime of x. For that to be true, that means, so we are looking to find an x in a to b, such for these two things to be equal to each other, h prime of x has got to be equal to 0. That's what we need. Note, h of a would be equal to f of b minus f of a all times g of a minus g of b minus g of a times f of a by the definition of f of t. And so if we expand this, that's going to be equal to, just using simple algebra, that's f of b, g of a, minus f of a, g of a, minus g of b, f of a, plus g of a, f of a. And we have some cancellations. The minus f of a, g of a occurs twice, one with positive, one with negative sign. So we get f of b times g of a minus g of b times f of a. Also, if we look at h of b, that's going to be equal to f of b minus f of a times g of b minus g of b minus g of a times f of b. And again, distributing we have f of b, g of b, minus f of a, g of b, minus g of b, f of b, and then this will be plus g of a, f of b. So I believe these two will cancel with each other, and so we're just left with, if you will, the last term over there is f of b, g of a, and then minus this term here, which I'll rewrite as g of b, f of a. So what we find is that f of a is equal to, h of a is equal to h of b. We consider two cases. For h of t. Okay. The first one is if h of t is a constant, then h prime of t will be equal to 0, and that's for all t elements of the open from A to B. So, any x element of A to B will have the property that h prime of x equals to 0. So any one of these x's will work. Case 2, that is if h of t is not constant, not a constant function. Okay, we'll note that this whole interval in R is a compact space. That's from something we've done in Math Analysis 1. So we've got this A to B is compact, and H is defined. And continues on this compact set A to B, then h of t attains its absolute max and absolute min. And A to B. Since h of t is not constant, then then the absolute max and absolute min cannot both occur cannot occur at both A and B. So since h of t is not a constant, it does make some up and down movement off of A and B, which were the same. Okay? And so it might be the case that both or either A or B are max, or both A and B are min, but one of them can't be a max while the other one being a min at the same time. Okay. So what does that say? Thus, there exists an x. Now the x is in A to B, but it can't be A or B. So there exists an x element of the open interval from A to B, such that h of x is either a maximum or minimum. And since, and we should say they're local. It'll be local max or local min. Since h prime of x exists, then by a previous theorem we did last time, then h prime of x must be equal to 0. Now that's about what we did last time. So, for that particular x, there exists an x element of A to B such that f of B minus f of A times g prime of x will be equal to g of B minus g of A times f prime of x. And that's what we wanted to show. I conclude that theorem. The next theorem is called the mean value theorem. As I write this on the board, I want to remind everybody that what I'm doing is in our text. This is out of chapter 5, and you have that part of the text from when you took the course last time. And so these proofs are there. I'm just elaborating on these proofs in somewhat I should say, where I'm adding some details that I hope helps people understand. But the proofs are also in the text. Okay, so here's the mean value theorem. Here's what it says. It says, if f is a real continuous function on the closed interval for A to B, which is differentiable on the open interval from A to B, then there exists an x element of the open interval from A to B such that f prime of x is equal to well, here's the way it's written. It's written that f of b minus f of a will be equal to b minus a times f prime of x. Okay, let's look at the proof of that. So we'll let f be a real continuous function on A to B and differentiable on the open interval from A to B. Okay. Now, also note that g of t equaling to t is a real continuous function on A to B and differentiable on open interval from A to B. So, by what I call the Cauchy mean value theorem, that was the previous theorem, there exists an x element of A to B such that we write down that f of b minus f of a all times g prime of x will be equal to g of b minus g of a times g prime, f prime of x. Note, g of b, that's equal to b, and g of a, that's equal to a. And since g of t was t, g prime of t equals to 1. So we have f of b minus f of a times, it says g prime of x, but that's just a 1, is equal to, well, it said g of b, but that's just b, minus g of a, that's just a, times f prime of x. And that's what we wanted to show. A lot of times when we rewrite this, is that f prime of x will be equal to f of b minus f of a all over b minus a. That's the way we often rewrite this. Okay. Here's our next theorem. It says, suppose f is differentiable and the open interval from A to B. Okay, then we have the following three facts. Part A, it says if f prime of x is greater than or equal to 0 for all x in A to B, then f of x is monotonically increasing. That is, it's never going down. I say the same, it's never going down. Part B, if f prime of x equals to 0 for all x element of A to B, then f is a constant. We're talking about on A to B. This is increasing on A to B. And part C says if f prime of x is less than or equal to 0, and that is for all x element of A to B, then f of x is monotonically decreasing on A to B. Well, we're just now introducing these words, or saying these words for the first time in a long time, and that is a monotonically increasing and monotonically decreasing. What does it mean to be monotonically increasing? That means that if you have function is defined on segments, so from A to B, a real value function, the numbers in between A and B. Then to be increasing is if you take any two values in between A and B, one value smaller than the other, then f of the function evaluated at the smaller value is less than or equal to f evaluated at the bigger value, input value. That's what it means to be increasing, so less than or equal to here. Where here the inequality flips. F of the smaller guy is going to be bigger than or equal to f of the bigger input value. So let's do proof. Let's suppose f is differentiable on or in A to B. Now for part A, we'll suppose f prime of x is greater than or equal to 0, and that's for all x element of A to B. Okay, we want to show f of x is monotonically increasing. So let's let x of 1 and x of 2 be elements of A to B, with x of 1 being less than x of 2. We want to show that f of x of 1 is less than or equal to f of x of 2. Okay, so here's what we do. Since f is differentiable on a to b, and we have a is less than x of 1, is less than x of 2, is less than b, then f is differentiable on the closed interval from x of 1 to x of 2. So from the mean value theorem, we can apply the mean value theorem to f. Why? Because f is differentiable on the open, and since it's differentiable on the closed, that means it's continuous on the closed. We'll say there exists a y, element of x of 1 up to x of 2, such that f prime of y equals to, so here it's f of x of 2 minus f of x of 1 all over x of 2 minus x of 1. Now look, x of 2 minus x of 1, that's positive. Now note, x of 2 minus x of 1 is greater than 0, and f prime of y has to be greater than or equal to 0. So, f prime y times this x of 2 minus x of 1 is going to be greater than or equal to 0. So that means that f of x of 2 minus f of x of 1, the top here, had to be greater than or equal to 0. So f of x of 2 is greater than or equal to f of x of 1. So f is monotonically increasing. Okay, part B. Okay, we're going to let f prime of x equal 0. We want to show that f is a constant on A to B. Well, note, we'll let x of 1 be less than x of 2 be points in A to B. Again, since f is differentiable on A to B, then f is differentiable x of 1 of x of 2. So applying the mean value theorem, to f on x of 1 and x of 2, there exists a y element of the open interval from x of 1 to x of 2 such that f prime of y is going to be equal to f of x of 2 minus f of x of 1 all over x2 minus x of 1. So we know that f prime of y in this case is 0. So f 0 is equal to f of x of 2 minus f of x of 1 all over x of 2 minus x of 1. So that says that 0 is equal to f of x of 2 minus f of x of 1. So that says f of x of 2 equals to f of x of 1. Now, x of 2 and x of 1 were just arbitrary numbers in A to B, and we showed that f of them are equal to each other. We know that these two numbers, x of 1 and x of 2, are not the same. So since these values were arbitrary, what we're getting at, f of x is constant on A to B. Now, the last part was about if the derivative was negative, then we want to show the function of monotonically decreasing. And here I will, if this is left to students, and it'll be part of the first homework assignment. Prove that. And of course it works most like what part A did. Next, I want to list a theorem having to do with the intermediate value property for derivatives. Here's what it says. It says, suppose f is a real value differentiable function on the closed interval from A to B. And suppose f prime of A is less than L, which is less than f prime of B. So this is some number in between the derivative at the endpoints of the interval. Then there exists an x element of A to B, open interval, such that f prime of x equals to L. Okay. As I said, this is known as the intermediate value theorem for derivatives. it's based on the function being differentiable on this closed interval, okay? And a similar statement holds true for the situation where f prime of A is going to be greater than lambda, which is going to be greater than f prime of B. So we're just looking at kind of a specific case here where our endpoints, the derivative, in this case, the derivative of the endpoint, the left endpoint is less than the derivative of the right endpoint. Okay, we want to prove this. Here's the proof. We put g of t equaling to f of t minus lambda times t. So g prime of t will be equal to f prime of t minus lambda. And g prime of A will be equal to f prime of A minus lambda. And that's going to be less than 0. The reason it's less than 0, of course, is f prime of A is less than lambda. Lambda's the bigger guy. Okay. So what that says is that the limit as t goes to A from the right of g of t minus g of A all over t minus A, that guy has to be less than 0. So this part right here is the derivative of g acting on A. And so this guy is positive. This guy is going to be I'm going to have to be negative since the whole thing is negative. Okay? So there exists a t sub 1 element from A to B such that g of t sub 1 minus g of A is going to have to be less than 0. So that says g of t of 1 is going to be less than g of A. Similarly, g prime of B, working with it, is going to be equal to f prime of B minus lambda, and that's going to be greater than 0. So there's going to exist well, let's write it down this way. So the limit as t goes to B from the left of g of t minus g of B all over t minus B, that's that derivative. It's going to be positive. But this guy's going to be negative. So this guy's going to be positive. But since this guy's negative, there exists a t sub 2 of A to B such that this has to be negative. So g of t sub 2 is going to be less than g of B. So since G is differentiable on the closed interval from A to B, G is compact. G is continuous. On A to B. Okay. So that means G attains its minimum on A to B. Since G of A and G of B are not minimums, and that's what that previous work showed, then that means there exists an X element of A to B such that G of X is a minimum. So since G is differentiable, G prime of X exists, and so since it's a local minimum, then G prime of X must be equal to 0. So what does that say? So that means that F, remember what G was defined to be. This says that F prime of X minus L has to be equal to 0. So that says that F prime of X has to be equal to L. And that's what we wanted to show. Ladies and gentlemen, the next thing we're going to do is L'Hopital's rule, and that's an application of the derivative for real value functions. It is a long statement, it's a long theorem, and what I'll do is I'll start by stating it next time and doing some examples and improving it. So that'll end lecture 4, and we'll start lecture 5 next time. Thank you.